SwayamPrabha. Digital India. Educated India.
We begin the lectures of week 8, and in the first lecture we will begin discussion about Inviscid high temperature equilibrium flow. Let us have a quick look at the contents of week 8. We begin with an introduction to Inviscid high temperature equilibrium flow, followed by properties of high temperature equilibrium gas mixtures, to begin with in a general framework and then discussing about air in particular. Then we would move to governing equations for this flow and as it applies to different kinds of canonical flows like normal shocks, oblique shocks, nozzle flows and blunt body flows. We will try to explain and understand what is meant by equilibrium and frozen flow, and we would also look at some numerical simulation results. To introduce the topic, we would like to state that high temperature equilibrium flow has to satisfy the following two requirements of equilibrium, namely local thermodynamic equilibrium and local chemical equilibrium, which are to some explained and elaborated under these two bullet points. So, let us look at local thermodynamic equilibrium first, and we of course have a flow in mind, though in the beginning we will discuss more about the thermodynamic or chemical equilibrium aspects as if it applies to a stationary medium, but then we would also like to extend that concept to flow problems involving flow equations. So, local thermodynamic equilibrium, in order to satisfy this requirement, it should have a local Boltzmann distribution at each and every point of the flow field at the local temperature T. The flow properties are naturally going to vary from point to point in the flow field. If you recall flow past a normal shock or oblique shock or a blunt body flow or nozzle flow, because of the variation of the geometries or nature of the waves, the flow properties can change from one point to the other or from one region to the other. But all the way through, the above requirement of thermodynamic equilibrium would have to be satisfied when we deal with such problems. So, that is the point that is made over here. So, it has to be satisfied at every field point. At each point in the flow, the energy of each species also has to be given by the relations that we derived in week 6 for both atoms and molecules when we discussed about microscopic thermodynamics or statistical thermodynamics. We will have a quick recapitulation of all this over the next few slides. As far as chemical equilibrium is concerned, we know that high temperature flow is going to be a reactive flow in general, and the flow has to be in local chemical equilibrium, means that at each point in the flow the chemical equilibrium calculations have to be remaining valid. We recall about equilibrium constants being used at the local values of T and P. So, these concepts were initially introduced in week 5 and week 6 from the classical thermodynamics as well as statistical thermodynamics point of view. We are also going to briefly discuss about these issues. So, keeping that in mind, we first look into part A, the local thermodynamic equilibrium. Again, a quick recapitulation will be really useful at this point. We have been talking about the Boltzmann distribution, which is a population distribution of particles distributed over different energy levels, which puts together the Bose, Einstein and Fermi-Dirac statistics under a single umbrella and works for high temperatures and low pressure ranges, where we have a unique statistics. So, this is the Boltzmann distribution we recall, and in the denominator of the Nj star expression, where the star of course works for the equilibrium, we have the Q, which is the partition function, and we were talking about the local value of temperature, which of course figures in these expressions. We have seen the use of partition function in obtaining thermodynamic variables like internal energy, enthalpy and so on, and we recall having learnt some of the basics of quantum mechanics or invoking some results of quantum mechanics for obtaining the sensible energies in different energy modes, that is the energy content above 0 point energies, and these expressions were substituted to obtain the energies in terms of the Q, the partition function. So, you may recall that we segregate the energy into two portions. One is the 0 point energy, which is of course a fixed quantity for a defined gas molecule, while the other part contributes to the sensible energy, which is clubbed under this bracket, where you entertain the translational, rotational, vibrational as well as electronic energy modes. And with this approach, we were able to demonstrate how the thermodynamic properties of a single chemical species gas can vary as a function of temperature. Now, when we talk about equilibrium of a gas mixture, of course, all this has to be translated into the mixture plane, where a number of chemical species exist. So, in this week we will try to understand how the properties of such a gas mixture can be worked out. From the point of view of local chemical equilibrium, we recall having come across this expression for entropy of a gas mixture comprising of a number of pure species, and therefore, we had derived the expression where contribution of number of species were taken, which come under the summation sign indicated by I, and we see that the entropy basically comes out as a function of temperature as well as the individual partial pressures of the species in the gas mixture. So, we have to move closer to obtaining the properties of the gas mixture. Till now we have gone some distance, but in this week, as I said earlier, that we have to focus on that. The condition for chemical equilibrium was expressed through the Gibbs free energy, and that was from a classical thermodynamics point of view, where we found an expression for the entropy production due to presence of chemical non-equilibrium, and then we argued that when equilibrium exists, chemical equilibrium exists, the entropy generation due to irreversibilities induced by non-equilibrium have to uniquely go to 0. Thereby, we ended up getting a condition for equilibrium chemically reacting gas mixture in terms of the Gibbs free energy, which figures over here in the expression. We showed that the change in the Gibbs free energy for a fixed pressure of 1 atmosphere is nothing but the change in the Gibbs free energy between the products and the reactants. And we finally ended up defining equilibrium gas constant or other equilibrium constant related with the chemical reaction, which we define as Kp, where it is found to be a function of T, because we have already set the pressure to a constant. So, though G is a function of both P and T, since pressure has been fixed, the Kp happens to be purely a function of T. So, this is how we were able to introduce equilibrium constant for the chemical reactions occurring in an equilibrium gas mixture from a classical thermodynamics point of view. From statistical thermodynamics point of view, again we can derive an expression for the Kp, but that involves some more effort, and also due to paucity of time we will not be able to do that. So, when we have a generic chemical reaction where reactants have been taken to the right hand side, we are able to write it down in this form, where the Ai's are the species and the nu i's are the stoichiometric mole numbers for the different species. Then based on this chemical reaction form, we can show that the equilibrium constant can be expressed in a form where the partition function plays a big role, and by definition it is a product of the partial pressures raised to the stoichiometric mole numbers of the different species. And when we apply statistical thermodynamics, we can show that the Kp comes out to be in this form, where we have a product of the partition function for each one of the species raised to the stoichiometric mole number for each species, and the remaining terms are in a product form which act on that pi term. The delta epsilon 0, which figures over here, is the 0 point energy of the products minus the 0 point energy of the reactants. Based on these principles, we can potentially think about obtaining equilibrium composition of a high temperature gas mixture in general. In particular, we are interested with high temperature air in the domain of aerodynamics. So, if air is heated in this temperature range at 1 atm pressure, we find that chemical reactions occur between oxygen and nitrogen, leading to formation of various species. These are the most important ones, and if we are able to keep the temperature and pressure stable and the gas gets long enough time so that the chemical reactions are occurring an equal amount in both the forward and reverse directions, then chemical equilibrium is said to have attained. That means, the net reaction rate would then tend to 0. This is typically where chemical equilibrium is established. Continuing with that point, at a given temperature and pressure, the specific fixed amounts of the different species would constitute the gas mixture. So, that is the broad definition. From statistical thermodynamics point of view, the system would attain chemical equilibrium when maximum number of microstates, that means the W max condition, is achieved. The gas particles of each species would be distributed over their respective energy levels according to the Boltzmann distribution, which we have been looking at a few minutes before. So, we once again visit the most important equations which are relevant over this temperature range for 1 atm pressure. If you alter the pressure, then either the reactions may be inhibited or accelerated based on whether you increase the pressure or you decrease it. Accordingly, the partial pressures of the different species would also vary, and then there is This system of equations that we had used in order to find out the composition of high temperature air, you recall having seen this in earlier lectures, but it is a good time to recap once more that we have the Dalton's law of partial pressure to be satisfied, followed by the equilibrium constant for different chemical reactions, which we left behind in the previous slide, based on the partial pressures of the products and reactants, and the Kp values can be obtained from the Janov tables, for example. The mass balance equation, emphasizing that the number of oxygen and nitrogen nuclei have to be conserved, and then electric charge conservation also has to be ensured, because you have a plasma where charged species are existing. Based on these, the different simultaneous algebraic equations have to be solved to obtain the unknown partial pressures. Incidentally, for the system that we have considered here, we see that there are 7 of them, and if you have sp number of species and any number of elements, then we know that sp minus any number of independent chemical equations have to be taken for equilibrium reactions. This is not true for non-equilibrium, which we studied in the previous week. And then we find that for high temperature reacting air, for the model that we considered, the sp was 7, the Ne was 3, and thereby we had 4 independent chemical reactions. And based on that, we should be able to work out the equilibrium high temperature air composition in terms of its chemistry over a fairly wide range of temperatures that is shown in this chart at 1 atmosphere pressure. Based on all these basics, which we quickly recapitulated, we would now like to address the question that how do we go about addressing the point that thermodynamic properties of a high temperature equilibrium chemically reacting gas mixture may be obtained. If you recapitulate, in week 6 of the course, we first learned how to calculate the thermodynamic properties of a single species using the statistical thermodynamics approach. And then if you consider both weeks 5 and 6, we discussed how to calculate the composition of an equilibrium chemically reacting gas mixture. So, in one we learned properties of single species, in the other we learned composition of an equilibrium chemically reacting gas mixture. And just to recap, the equilibrium constant for the chemical reaction was either based on the Gibbs free energy or the partition function based on your classical or statistical approach. And now we would like to put the things together so that we are able to obtain the thermodynamic properties not of a single species, but of that of a gas mixture, and in the process also obtain its composition, which we have already learned to do here. So, we are mainly trying to bridge the gap from the thermodynamic property point of view, which earlier we have done for a single species, we now would like to do it for a gas mixture. We will begin with the use of enthalpy of the gas mixture to obtain the thermodynamic properties. Like we do with enthalpy, it can be similarly done with any other thermodynamic property as well on similar lines. If we start with enthalpy, we will find that we will ultimately be able to see a connection with the heat of formation concept, which we have learnt earlier and was discussed in week 5. If you go on a per unit mass basis of the mixture, then you can write down the enthalpy of the gas mixture in this manner, either in terms of the mass fraction of the species, or you can go by the mole mass ratio. So, here in that case with the mass fraction you will have enthalpy per unit mass, and when you go by the mole mass ratio you get the enthalpy per mole. You recall the nomenclature that we use an under case or lower case for unit mass basis and upper case for per mole basis. So, we continue to follow that nomenclature. On a per mole basis we can write the enthalpy in this manner. So, remember that here it was the H expressed in a per unit mass basis. Now, we want to express H on a per mole basis, and therefore, we switch from eta I to x I. So, this was mole mass ratio, while here we are using a mole fraction. Now, the detailed expression for H I can be written in this form, where we segregate it into two parts. One is the sensible enthalpy and the other is the 0 point energy of the different species. So, we associate a I in the suffix indicating that this will happen to each species. This is the absolute enthalpy, this is the sensible enthalpy, and this is the 0 point energy, and all of them are per mole of I. The concept of sensible energy, of course, we had introduced in statistical thermodynamics. We have also recapitulated it in week 8 as well. Based on that concept, we can recall the definition of capital H in terms of internal energy and the product P v or R T, where R is of course the universal gas constant, because this is the equation of state written on a per mole basis, and we want to plug that into this equation, where we have written the sensible energy in the sense that we have taken a difference of the H and E naught like we wrote over here. So, we are repeating that over here, now expanding in terms of internal energy and R T. The difference that we take between H and E naught, that reflects on a difference between E and E naught on the right hand side. And now, it is a good point to recall the expression for sensible energy for molecules and atoms on a per unit mass basis. It can be easily extended to per mole basis. So, this is something that we had discussed at length when we were discussing statistical thermodynamics in week 6. So, we saw the contribution of different modes of energy in the total energy expression in terms of translational, rotational, vibrational and electronic. All 4 modes can potentially exist for molecules, and we discussed that only 2 at most can exist for atoms, namely the translational and the electronic. Now, based on the above equations which were written for unit mass basis, we can extend it to unit mole basis. And where does it help us? It helps us in writing the H minus E naught expression. Remember that the expressions that we wrote over here were considering the sensible energy, which means the E naught part was already subtracted from the E, and therefore, the same thing applies over here. Note that we have changed the specific gas constant to universal gas constant when we move from unit mass to unit mole basis. Now, it is quite obvious from this expression that H by minus E naught for each species is definitely a function of temperature. We recall that E in general is written in a form like this, and further the electronic energy, though we do not see an explicit dependence of that part of the energy on temperature, we may recall this form where we remember that the different terms which figure in the partition energy for the electronic energy mode also contain the temperature dependence, which finally means that the electronic energy also is a function of temperature. Put together, it is evident that H minus E naught for every species is a function of T. Coming to the dependence of sensible enthalpy on temperature, this is a very important representation that we should look at. So, the y axis shows the absolute enthalpy of the species and the x axis shows the temperature on absolute scale, and this curve basically shows the absolute enthalpy content. The dotted line shows the 0 point energy of this particular species I, which is showing the level E naught I. And if you subtract the E naught I from the H, which is the absolute enthalpy or H I, then you end up getting the sensible enthalpy of the species, which is nothing but the portion which is above the dotted line or the E naught I level. So, that is basically the sensible enthalpy variation with temperature. Since it is difficult to obtain E naught I, we have to find a way where we can evaluate enthalpy without directly encountering this difficulty of trying to obtain E naught I, the absolute value of that, for which we shall evaluate enthalpy in terms of change, let us say between 2 points of the flow field. So, when the flow moves, you have 2 points 1 and 2, and you try to define the thermodynamic parameters at these 2 points and take their difference and try to approach the problem. So, we call those 2 points as, let us say, A and B in a flow field, and we write down the enthalpy at the point A as a summation of eta I H I summed over all species at that point A, and then that brings in the expression for enthalpy in terms of the 0 point value as well as the sensible part. So, we have segregated it into the sensible energy at A and the 0 point energy at A. The same process applies to the point B. So, this is the equation that you can write when applied to the point B in the flow field, and thereby you will end up getting an equation H B is equal to H S E B plus E naught B. The subscript S E stands for sensible energy. Now, if you take a difference, that gives you the change of enthalpy between the points A and B, and that is expressed in terms of change in sensible enthalpy between the 2 points and the change in 0 point energy, which basically means you do not any longer have to calculate the absolute value of the 0 point energy, but you just need to evaluate the difference. So, this is an equation involving the differences. To proceed further, we have to introduce an important concept here, that is what is called as the standard heat of formation. We will look at what the concept is. So, when we consider a chemical reaction which represents formation of a single chemical species from its elements at standard conditions. So, we would call them as, say, constituent elements which form a part of this species, and when they are existing at standard conditions and they are forming this particular species, the heat of reaction has a special name that is called as the standard heat of formation. The name standard comes from standard conditions, and the heat of reaction when you are forming the species from its constituent elements has a special name, heat of formation. By standard conditions, we mean conditions of stable elements which are the constituent elements at standard temperature of 298.16 Kelvin. That is what we mean by standard conditions. So, there are two aspects. One is that the constituent elements which exist in their stable form under 298.16 Kelvin temperature have to be considered, and the reference temperature happens to be 298.16 Kelvin when you do the calculations. When you take the stable form of the elements, you have to keep in mind, for example, at 298.16 Kelvin, if you are considering molecular oxygen or nitrogen, that is what is the form in which oxygen and nitrogen would exist under these standard conditions. They would not exist in the atomic form. They are expected to exist in their atomic form at much higher temperatures, and therefore, if you are trying to calculate the heat of formation, you need to consider them in that form if they form part of the constituent elements for a certain chemical species. That is the point we are trying to raise. Therefore, when participating in a chemical reaction, oxygen or nitrogen, they cannot participate as atoms at standard conditions, they have to participate as molecules. So, that is the message we are trying to send. We will look at more about heat of reaction and then how it helps us to understand the heat of formation in the next lecture. So, let us conclude this lecture by saying that we discussed equilibrium requirements of high temperature gas mixture, the thermodynamic and chemical equilibrium aspects were discussed in detail. We did a lot of recapitulation also in the process, and discussion was initiated on thermodynamic properties of a high temperature equilibrium chemically reacting gas mixture. We will take it further in the upcoming lectures. Thank you.